One of the most intriguing results from this paper is how simply repeating the input tokens during pre-training can lead to better model performance, almost like giving the model more practice on the same material to deepen its understanding. They show that this repetition scales up the training effectiveness, resulting in lower loss and improved accuracy on tasks like reasoning benchmarks.
Exactly, and they achieve this without bogging down the model with extra baggage. The key method here is the Parallel Hidden Decoding Transformer, or PHD transformer. Imagine the transformer as a student taking notes during a lecture. Normally, it keeps all notes in memory, which can get overwhelming. But PHD transformer uses a smart KV cache management strategy. It's like only saving the core lecture points and tossing the temporary scribbles right away. This way, they distinguish between the original tokens, which are the main content, and hidden decoding tokens, which are like quick side thoughts, and discard the latter immediately to keep memory efficient.
Building on that, another exciting result is how this approach maintains strong performance on long-range dependencies, meaning the model can still handle connections across distant parts of the text, just like piecing together a long story without forgetting the beginnings. Their experiments demonstrate consistent improvements across various benchmarks, making the model sharper at tasks that require deep reasoning.
Right, and to make this even more efficient, they introduce variants like PHD-SWA. Think of it as the model focusing on a sliding window of attention, similar to how you might only pay close attention to the last few sentences in a conversation to catch local details, while still keeping an eye on the bigger picture. This helps preserve those nearby dependencies without overloading the system, all while sticking to the efficient KV cache strategy we mentioned.
That's a great analogy. On the flip side, they also show how naive methods of repeating tokens can slow things down a lot during inference, like causing delays in generating responses. But with their PHD-SWA variant, which uses chunk-wise sliding window attention, the model avoids that buildup. It's like breaking a long road trip into manageable chunks, so you don't have to plan the entire route at once, leading to faster pre-filling and decoding times without sacrificing accuracy.
Absolutely, and the accomplishment here is that PHD transformer keeps the KV cache the same size as a standard transformer, which is a big win for efficiency. By only holding onto the essential tokens and ditching the rest, it's like streamlining a backpack for a hike. You carry just what you need for the long haul. This makes length scaling during pre-training not only effective, but also practical for real-world use, without the usual trade-offs in speed or memory.
To wrap it up, the paper's key takeaway is that you can scale up the length of sequences in pre-training to boost reasoning and overall performance, much like extending a workout routine for better endurance, but without the inefficiencies that typically come with it. The PHD transformer's innovative cache management and its variants could really change how we build large language models, making them more powerful and user-friendly for applications like advanced math problems or complex text generation.
Exactly, Ben. In essence, this work highlights the potential of efficient length scaling in pre-training, showing that with clever techniques, we can enhance models' abilities while keeping things fast and resource light. It's a step forward for ML research, encouraging more exploration into how models handle and remember information over longer sequences.